Cool. So hello, my name is Liam Foster. Welcome to my TED Talk. We're going to be discussing the manifestation of beauty in physics, based off of the first slide. Anyway, is this the go button?
It's the bottom one.
Bottom one? Cool. So in order to discuss what beauty is in physics, we have to first discuss what beauty is through the lens of physics. And to do that, we're going to parameterize beauty into productivity, simplicity, and elegance. Productivity is how much a theory can explain. If it can explain more things, more productive. If a theory is simple, then it doesn't have unnecessary pieces to it that can be cut out in in simpler models. And elegance is the idea where when theories get unified, like when you have seemingly disjointed fields of physics come together, then it becomes more elegant. And that'll become more apparent with a couple of examples. So classical physics is where we're going to start. It's divided up into three main categories. You have mechanics, electromagnetism, and thermodynamics. We're just going to focus on mechanics and electromagnetism today. Thermodynamics, it's not that it doesn't fit this model, it's just that it's incredibly tedious. The guy that invented a lot of the frameworks that are used there, by the name of Boltzmann, ended up killing himself. And one of his students, who also pushed it a lot farther, ended up shooting himself. So we're just gonna kind of ignore that for today. Starting out with classical mechanics, you can kind of start out at the bottom because we don't know anything yet, right? Productivity, we don't have any productivity because we're not explaining anything yet. The simplicity doesn't even make any sense because we don't have any framers to base that off of. And we haven't combined it with anything for the elegance component, so that doesn't make any sense to talk about yet. To start out, we're going to talk about three parameters. You have position, velocity, and acceleration. The reason that position is an S is because we ran out of letters twice. Because you'd think that it would be a P, but that's what momentum is, because momentum is an M, or is an M, because that's what mass is. It'd be nice if there's more than 26 letters. But anyway, we're also going to have to define a couple of mathematical frameworks. You have a derivative and an integral. A derivative just finds essentially the slope of a function at some point. And an integral in this context undoes that. It's an antiderivative. What an integral can also do is you can use it to add up things in a really fancy way. And it essentially becomes an area under a curve, which is kind of fun. But with these tools, we can take those parameters that we had and build equations of motion with them. So the velocity is the rate of change of position. The acceleration is the rate of change of velocity. So we can use derivatives to explain this mathematically. And then integrals you can use to undo it. And then also, to top it off with making it so we can have forces play into this, we have Newton's second law of motion, which is just inequality between force and mass and acceleration, which is fun. So with this, we actually get a lot of productivity. We're able to explain most of movement in classical physics with this. It's pretty simple, given that it's just some simple calculus frameworks and a couple of algebraic equations. And it's really elegant because it's one of the first times that we've applied laws of physics here on Earth and also in the cosmos. Because before this, and I mean, of course, this had been coming up. I mean, there's a paradigm shift that took a while here. But it's really cemented this idea that physics applies everywhere in the universe, with having the same laws of physics govern what we see in the heavens and here on Earth, because that wasn't really something that was apparent at the time. And that brings us to classical electromagnetism. So we start at the bottom again. Don't know anything. And then, and we're going to start out with this equation here, which looks nasty, but it's essentially an analog to Newton's law of universal gravitation, which is just saying that those two Q's are charges because we ran out of C's somewhere, and then the K is just a constant that is the 1 on 4 pi epsilon naught that you see in the right side of that. All it's saying is that if you have higher charges, you have a higher force. If they're farther away, then the force is lower. Keep an eye on those epsilon naughts. You also see a mu naught later. The epsilon naught is actually, it determines almost the strength of the electrostatic force, which is neat. But just keep an eye on those, it'll be cool later. So with this, we have an increase in productivity because we can explain more now. We can put in a mathematical framework how charges interact. It's actually fairly elegant because it's this really cool analog. It's a pretty neat symmetry between it and classical mechanics, which is where Newton's law of universal gravitation comes from. It's not simple because we have to deal with another equation, but That brings us to this. This came about when a guy essentially, a guy named Oersted, saw that if you ran a current through a wire, then it deflects a compass needle. And it's really, really neat because it's starting to show this, this bond between electrostatics and magnetism. But you can just kind of ignore that last part. You don't need that until you get to like second year of college physics. But anyway, all this is saying is that if you add up all the magnetic field along a loop, then it's equal to some constant times the current running through that loop. So if you have a wire, what it's saying is that along a loop you're going to get a magnetic field around it. Right, so this is saying that a moving charge generates a magnetic field, which is really cool. It's really demonstrating this bond between those two. Those constants keep popping up again. Keep an eye on those. They'll be neat in a sec. So it's more productive now. We can now see that we can generate magnetic fields with an electric current. It's more elegant because it's again demonstrating this bond between those two fields, and it's less simple because we have to deal with another equation again. And this brings us to like the last one of this set of equations that we're going to talk about. This is Faraday's law, and this is really cementing that bond between electromagnetism or between electrostatics and magnetostatics. The flux derivative thing there is essentially just saying a changing magnetic field. It's saying that you get an electromotive force, which is what the weird E-looking thing is. You just get you get an electric field essentially when you have a changing magnetic field. Is what this is saying, which really like cements that bond between those two fields, which is really, really cool. Right, and now we can explain more things. This is the foundation for electric power, essentially, where if you spin a magnet inside of a coil of wire, then you're going to get an electric force, which is going to make it so you can push electrons through that wire, so you can like have these lights and a projector and things, and lasers. And so it's more productive now, which is cool. It's really, really elegant because it really like finalizes this bond between electrostatics and magnetism. And it's less simple because we have to deal with another equation again. And that brings us to these, where we can put them kind of all on one page. These are Maxwell's equations, and they're really, really cool. And you've actually seen the majority of these before. That first equation is actually just a reformulation of Coulomb's law, which is the first one that we looked at. The second one is just saying that you can't have magnetic monopoles, which means it's just a barrier against having perpetual motion, which would break conservation of energy. These constants pop up again, so keep those in mind. But what this does is it makes it so we put all of these equations on the same footing, right? So we have a very similar format for all these equations that describe how electromagnetism operates, which is really, really cool. It's incredibly productive. We can now unify all these. You saw like the last equation. Let me go back for a sec. Can I go back? Oh, that's a laser. Okay. That last equation is just, it makes it so we now have an integral representation of Faraday's law, which makes it so it's more powerful. And you can use it for more things. And this makes it more productive. We can now use these equations together to describe really fairly complicated systems. It's really, really elegant because now all these equations are on the same footing. They're all very, very similar integrals. And the simplicity actually goes up again because of that, because now you have just this set of 4 equations that describes an enormous amount of physics, which is really, really cool. And those constants that I was having you guys take a look at, this is a really, really cool equation here, because it's saying that the speed of light, which is the c, I know this is kind of a gear shift, but that's kind of the point, because all of a sudden the speed of light falls out of these equations, right? Which is crazy, right? It even has the units of meters per second if you plug in the units, which is wild, right? We combine electrostatics and magnetostatics into electromagnetism, and all of a sudden light falls out, which is crazy. So we have these 4 equations that are now giving us a basis for how light works, right? And if you remember from chemistry, light is an electromagnetic wave, right? And that's what this means, is because with things like Faraday's law, where you have a changing magnetic field generates an electric field, right? So if you have a changing magnetic field in such a way that it generates a changing electric field, then that can then generate a changing magnetic field, and they can self-propagate, and you get self-propagating electromagnetic waves, and that's what light is. And you'll see here that there's no considerations for what frame of reference this is in. And this really throws it at odds with classical mechanics, because classical mechanics says that you have to be moving in reference to what light moves through. Because the way that classical mechanics represents the motion of waves is that they have to be transmitted through a medium. And just like sound from my voice transmits through air, the light had to transmit through a luminiferous ether. And the Earth orbits the sun, so you'd expect for there to be an ether wind. You'd expect for the speed of light to actually change during different times of year. And with Maxwell's equations, it's a constant speed of light no matter what reference frame you're in. And this is a really fundamental piece of physics, is that there's no preferred reference frame. Right? Here on Earth, it seems like we're stationary, even though we're spinning around really fast and going around the sun. Right? That doesn't mean that we're all right. So that's pretty neat. But we would expect to be able to see this changing speed of light if that were to be the case with the ether wind and such. So these two guys, Michelson and Morley, developed this thing called the Michelson-Morley Experiment. Go figure. Where essentially you have a light source, it hits a beam splitter, hits two mirrors, the lights recombined, and you look at the recombinant interference patterns on a plate. Depending on this, you can tell whether the apparatus is moving because, with respect to the light, because the light will have to move farther to get to the plate on the side that it's moving towards, is the idea there. And this is often referred to as it's like the most famous failed experiment of all time, because they went out to try to find the ether wind to prove that it worked the way it did. They found no ether wind whatsoever. They actually found that the speed of light was incredibly constant for no matter what time of year it was, which is really, really cool. And that means that electromagnetism had kind of beat out mechanics in this fashion. All of a sudden, we had a constant speed of light across all these reference frames, which is really weird, right? It kind of throws classical mechanics for a loop, right? And it doesn't matter how productive and simple or elegant your theory is if it doesn't work, right? So we needed to take into account these things to make it so we could have a more comprehensive model of classical mechanics. So this patent clerk guy fixed a lot of it. So in Einstein's theory of special relativity, there are two postulates that are laid out. One, it's that the laws of physics are the same in all inertial reference frames, which is the same. That idea had been around for hundreds of years. It was, Galileo essentially came up with it, with essentially that there's no preferred reference frame that everything moves in respect to. You can still model things. Like if I'm moving, I can model all of physics around me with that taken into account. There are reference frames where it's easier to model things, but there's none of them where it's impossible, which is really neat. The second thing is that the speed of light has to be constant in all these reference frames, which is really weird. What this is essentially saying is if you're driving in a car and you have a baseball and you throw it to a friend outside the car, then you add the velocity of the baseball to the car. But if it's at night and you turn on the headlights, then the speed of light for you inside the car is the same as the speed of light for somebody standing outside the car. So it operates on a fundamentally different playing field, which is really, really crazy. And what this means is that we have to actually fundamentally change how we think about time, how we think about things like length and mass, right? The little gamma, which is the upside down L-looking thing that's almost like a Y. We had to use Greek letters because we ran out of all the English ones. So what this means is that what that is where your velocity increases, that factor gets smaller, and when your velocity decreases, then it approaches 1. So you can see at low velocities with respect to the speed of light, you have no time dilation. Like the time of the moving person is the same as your time. There's no length contraction because, right, and so on and so forth. But as speed increases, those start to play a bigger and bigger role and change how these equations operate, right? And this, for the most part, fixed classical mechanics, right? You have more productivity because now we can explain the motion of these really, really fast objects precisely. It's elegant because it makes it so there's this extra added layer of symmetry between it and Maxwell's equations, that they're invariant under Lorentz transformation, that's what it's called, where the speed of light thing doesn't mess everything up, essentially. And you just have to add an extra letter, essentially. It's a little bit more of a pain to do the math with, but it's not adding a significant amount of extra junk to it to make it so it works again, which is really, really cool. And that kind of brings us to this point, where now we can compare our two graphs that we've made of simplicity and elegance and productivity over time for electromagnetism and for mechanics. Right, so we can draw lines on it. Sorry that they look like crap. It's because the computer can't run Photoshop, so I had to do it in the spreadsheets thing with the line. It sucked. So essentially what it says is that on a shorter time span, like for Maxwell's equations and for electromagnetism, we have increases in productivity and elegance as a theory matures, and then but a decrease in simplicity as we're adding things to it. And then we get to a point where we break down into a deeper, more fundamental level of knowledge, where the simplicity can go back up and we can discard extra things, which is really, really cool. For classical for mechanics, on a much larger time scale, we can see that physics has a slow growth of knowledge until we find out that there's something wrong, and we have to go back and fix it. And oftentimes, like with classical mechanics versus relativity, it turns out that what we knew was a limiting case of a bigger, more fundamental, more beautiful knowledge, theory of the universe. But what this means is that we can actually map our discussion of the electromagnetism onto special relativity and have this really cool idea of how knowledge progresses in physics, which is neat. And essentially what my question was is, can we use this to predict revolutions in physics and things along those lines? And it turns out that physics is really complicated and
who knew?
Likely to break past where we are, we're going to have to invent a new kind of mathematics. Nobody really knows when all this is going to happen. And also, we can't predict what's going to happen in the future with something like this based off of what has already happened. So while it's really, really fun, metaphysics, thought experiment kind of thing, but it doesn't have that much of an impact as a whole on how physics works. But yeah, that sums it up. Thanks for coming. Yep. Questions?
Thank you, Liam. Waiting for you to pull a sword out on us.